Hi, welcome to this webinar focused on MSC Apex, the new release Iberian Lynx for the aerospace industry. This was originally presented by colleagues at MSC Vidya Shankar and Zanlang Ying, but it's now been re-recorded to give improved audio quality by myself, Dr. Stefan Evans, and I'm the lead FEA engineer at Evotech CAE Limited, who run a number of training and webinar focused events for MSC Apex. Okay, so let's get started. So Apex for the aerospace industry allows you to achieve huge reductions in model turnaround time. We're talking 10x in a sort of conceptual term rather than discrete numbers, but everybody that uses Apex is very impressed with the efficiency gains that can be made with the tool set. Very easy and even enjoyable to use, so people can pick the software up quickly. Many liken it to a video game in the sense that it's fun to build models and run FEA over legacy tool sets, and that's certainly true from speaking to people that I know involved with Apex. It opens up the analysis process to non-specialists, so this can be by engaging non-FEA or younger, less experienced engineers into the analysis process. Easy to use software. There's the possibility to script within Apex very easily, so we can effectively black box process to non-specialists if they wanted to work in that manner for a given company. And there's flexible licensing access, so again using the MSC One licensing system we can open up multiple licenses to people relatively low cost, giving everybody a chance to use the technology. And then finally we've got very powerful analysis and automation techniques in the flexible architecture. As mentioned, the Apex is built with a very powerful Python-based API, application programming interface, allow you to customize and automate many processes in a manner never seen before with conventional FEA software. These capabilities are very prevalent in the aerospace industry. FEA is key in a lot of, well, in most development processes or strategies, and having a robust FEA tool that can both build and analyze models quickly but with good quality is key to that development process. Final thing to say here, Apex gives you, the engineer, the designer, whatever, the freedom, both in terms of modeling capability and efficiency, to develop your current and future products in a manner you've never seen before. Again, Apex is a tool that allows you to get the job done quicker. You can get your products out into the market quicker. So the Apex journey, Apex has been around for a number of years now, various different releases. So first of all, Arctic Wolf and Black Marlin release. So this is more sort of CAD to mesh type tool using the Apex modeler technology. Again, very easy to use, faster model preparation, faster to modify and update models. Then we moved on to a further set of releases whereby we can now embed, or we've got embedded the Apex structures framework, which allows us to get to from CAD to results in a much faster manner than previously, to allow us to run round design iterations, rapid redesign very quickly. Then we moved into the more recent versions of Apex, which has really integrated and revolutionized a lot of the CAD, CAE analysis and post-processing aspects into a single framework. And again, much of this hinges on the presence of the Python API to allow people to automate and customize the environment. And then from that we've got somewhat of a paradigm shift now. So rather than using the Apex structures solver, which is embedded within the Apex environment, we've now opened up with the latest release, Iberian Lynx, the concept of Apex and Nastran interoperability, which means we can write out model files externally to be solved in a MSC Nastran environment, and then those results can be imported back into Iberian Lynx to take advantage of the result exploration and post-processing technology within there. So in terms of product release and workflow, and this is very typical of a standard aerospace type organization, how they would work with technology. So a legacy non-Apex approach typically would involve Patran to build a model, Nastran to solve, and then Patran to post-process. We then moved into having Apex environment, so we can now use Apex in a companion basis. So a lot of the very efficient tasks that Apex is good at handling, such as CAD to mesh, model verification, some aspects of automation can be done very quickly in Apex, but then some of the further aspects such as model attribution and solver setup done back in the Patron environment, the use of an imported bulk data file. Then we go back into Nastran for solve, and then back out to Patron for post-processing. Then Apex is a full pre-processor. So as Apex is developed, we can now build the full entirety of the model, so composite materials, different loads and boundary conditions, a whole host of different model build meshing techniques available to allow us to do the full build or full pre-processor within a single Apex environment, followed by Nastran solve and then Patron post-process. And then what we've got now today, Apex for Nastran, with the dawn of the release of the Iberian Lynx version, where we can now pre-process and post-process in a single Apex environment, with all external runs done with Nastran, whether that's for to take advantage of high-performance computing or certification in terms of which solver has been used to generate the results. There's a lot more access between, or a lot more compatibility between Apex and Nastran today. So, functionality growth. So pretty early on, Apex in the companion sense, we have some keyword support, so we could build a mesh, we could propertize that mesh, certainly for metallic isotropic materials, and then export the resultant bulk data file into Patron for development, again, for maybe composite materials, further more involved or exotic loads of boundary conditions. And then as Apex has developed, so we're looking now at the Apex companion mode, so we can set up, we've got more keywords supported, we've got more analysis capability, so whether that's linear static, normal modes, linear buckling or frequency response, we can do that within the Apex environment. And then as Apex has developed into the full pre and post setup, we can now use Apex to fully build the model, Nastran to support to solve externally, and then Apex to fully post-process the data. Key things here that have come in at the Iberian Lynx release are the ability to explore results based on the MSC Nastran HDF5 result format output, and also orphan mesh support. You may or may not have come across this term, orphan mesh. I hadn't when originally exposed to this technology. It's basically the ability to import Nastran data, so typically a bulk data file where you'd have no geometry whatsoever, so you could take a legacy Nastran model, read that into the Apex environment, and then look at multiple tools to manipulate that mesh that's come in. So whether you wanted to refine the mesh in some regions, or even fully change the structure with the inclusion of some imported CAD or even geometry created in Apex, we've got orphan mesh support. And all of this technology is growing as we speak. So there's a very large development team that MSC have engaged, and we've got much more keyword support, much more exotic analysis and solution types, more result exploration, and certainly more orphan mesh support as we move forward with Apex from today. So how can Apex improve your productivity? Iberian Lynx opens up your FEA development. It basically allows you to do your full activity now, certainly for linear type solutions within the Apex environment. So Apex is implicit in your MSC Nastran workflow. It's undergoing continual development, as I mentioned, in terms of the development teams that MSC engage with, in generative model build and manipulation, analysis and result exploration with every release. So there's a whole host of new functionality coming in as per the release cycle that Apex has been distributed at. Apex's Python-based automation now offers build, but also analysis and result exploration support, and also key is the ability to customize the graphical user interface, the GUI, and even create user-defined tools for job-specific or even company-specific activities. The current and future development is driven by a desire to address key industry pains, allowing you to experience the full benefit of an Apex-focused workflow. Obviously, MSC are implicit within many of the world's largest, well, within most of the world's largest aerospace-focused companies, and we know where you struggle, what your pains are, and Apex has been developed in conjunction with those companies to give you a far better, a far more efficient user experience, to give you what you need from an FEA toolset. So we're going to look now at a number of aerospace-focused functionalities and workflows. I'll just move on to this very quickly. So we've got, first of all, the MSC Apex Nastran workflow. So Apex is now fundamental to your Nastran workflow. If you are, as I say, you need to use MSC Nastran from a certification or a legacy process requirement, you can certainly do this with Apex. So we have enhanced keyword support, both for reading models in and for exporting models. We have the ability to interrogate the Nastran format, the HDF5 result binary file, to take advantage of the powerful result exploration and also the Python automation within the Apex environment. And just a simple infographic here that shows over time. So in one of the early releases, Diamond Python supported a number of keywords, but as you can see, there's been exponential growth in terms of the Iberian Lynx supported keywords. And if you wanted to, you could look at the word cloud on the right hand side and see the various different words that are now supported. Okay, so we'll look at a quick screen recording of some of the Apex Nastran workflow. So first of all, we're going to import Nastran bulk data file from an external source. So this may be model from a legacy model or something we'd created previously within an Apex toolset. So we can preview the model as it comes in, so we can look at things like the keywords, the number of keywords, whether we want to bring them in. We can change the units at this level, so we could effectively go from an imperial or English unit system into a metric or vice versa. We can see things like the extent of the model in terms of its XYZ dimensions, properties, loads. We can organize the model, so here we're organizing by continuous mesh region. Simply import the model and in comes the model, and we can see in the model browser tree on the left hand side how the model has been effectively generated or archived, if you like, within to respect those individual contiguous mesh parts. We've got a number of connectors within the model, shown here, zero length R bars for this type of model. We can look at those explicitly. So we can see here we've got a local coordinate frame defined. Again, because these are zero length, they're all aligned with the global system. Looking at each of the parts, we can just show only the regions of interest, or the region we want to look at. So again, this is a typical wing box model from a typical airframe supplier. We can see, if we go into render mode, we can see the wing skins upper and lower, the spars, the rib layout, the trailing edge definition, what have you. So taking the wing skins out of view, and again we've got the cursor support, so we're not continually back and forth with the cursor to various forms which we need to find. So we can see here we've got a shell and bar topology, which is typical of a sort of aircraft or aerospace loads model, and due to the implicit Apex structures solver, we can run some of the verification loads. So here we're just looking at a free normal modes analysis, just to understand the behavior and how things are tied together for this type of component within the full assembly. And we can look at the mode shapes and the strain energy distribution. So modes 1 to 6 are rigid body modes, mode 7 plus are elastic body modes as per a standard verification type exercise, and we can look at the element strain energy, where that's peaking and what have you, just to make sure that the structure's behaving on a component level as we want, and then we can run that analysis for the full structure once we've got a good handle on how the discrete components are working. So once we've done that analysis, we can then export the model and then read in, rather solve externally, then read in the MSC Nastran HDF5 file format. We can see here just reading that data in, and now we've got full post-process capability to look at results in any way we wish based on the standard Apex approach, or even automate those using some of the Python API tools. So just looking at wing deformation and the stress distribution for a simple load case, but just illustrative of the type of thing we can do from that result post-processing. So moving on to a second screen recording. So this is now looking at how we would, just bear with me, play the video, how we would look at modifying the imported bulk data file. So we've got no component level geometry here. We've just created a single or simple volume to surround an area of the model which we're now going to modify. So we're going to show some of the orphan mesh and geometry tools. So first of all, we're going to remove an area of the model which we perhaps no longer want. So just delete the mesh definition. Again, back and forth, no back and forth to forms. We can do all of this from the cursor support, and just removing the full extent of the model, but retaining the area that we wish to work with for our subsequent model build. So just tidying up the model, and again there is Python API to support this if you wanted to automate this process. One good example would be to delete all the elements that don't sit within the bounding volume, but just look at some manual approaches here. So if we look at the wing skin, portion of the spar and one of the wing ribs, and we can look at the mesh, we can turn off the 1D display where we've got the bar elements acting as stiffeners, just showing only the spar and rib web for this region. And we're now going to look at some of the new geometry updates within Apex environment. So first of all, we're going to look at the faceted surface generation. So this is working in a manner that's not been seen in any of the CA tool set so far. We're creating geometry from mesh. People talk about CAD to mesh. We're working around it with this. So we've created faceted surfaces through all of that mesh. Obviously we're working with flat surfaces here. If we had curved or spherical surfaces, we could work at that level as well. So once we've got the surfaces created, we can delete the underlying mesh and then remesh at any element edge length we wish to. Moving on to the wing skin. So we're going to look at, rather than the faceted surface defined from the mesh, we're going to look at this in a slightly different way. So we're going to create a number of curves which connect the extremities of the surfaces. So just a simple, we're treating this as a simple flat surface at this stage, but obviously we could take advantage of a more detailed definition if we wanted to. So we're just basically creating splined surfaces, so rather splined curves on a node-to-node basis for the key regions which make up the mesh levels, and then we can delete the underlying mesh from the model browser tree, and we're now left with a series of curves. We can now loft, again a new function within Iberian Lynx, we can now loft a surface between two or more curves, two more non-connected curves, and then we can control the edge tangency and what have you to control curvature. Obviously they're relatively flat in this case. So just showing the whole thing, we can now see how we've got new geometry, and then we can remesh that geometry based on our desired element edge length. We look at properties. It's retained the properties for the faceted surfaces, but we need to redefine those for the surfaces that have been created by the lofting exercise. Okay, so moving on to typical workflow in the aerospace industry. So Apex has got the power to support many different workflows. Again, we've seen powerful automation for all aspects of build, solve and result exploration. We're going to look at one process which is prevalent through many airframe developers, the Wingbox global local paradigm as it were, whereby we would have a global model or a GFEM, global FEM definition for the full structure, a wing in this case, and then we might wish to develop a local detailed model, DFEM, to then tie into that GFEM to understand local response for the newly modified or more refined region. Obviously this is a fairly crude example, but is illustrative of that approach. Okay, so we're just going to again look at the screen recording. So here we have the same wing global FEM model read in that we looked at previously, just showing some of the topology at a rib to spar joint definition, and then we've read in the detailed region, and this has been developed in a manner similar to what we looked at with the previous screen recording. So we've got a newly meshed wing skin, rib and front spar. We've included some local detail, and we've modified some of the faceted or lofted surface geometry to give us cutouts at the rib to spar interface. We've included fastener locations which the mesh has respected using some of the mesh technology within Apex, and once we've got that, we're pretty much ready to go and to tie things together. So on the right hand side now we can see an example of the custom tool palette where we've customized Apex to work with an external script in this case, which is going to look for hard points within the mesh, look for adjacent points which are within a given tolerance, and then join those up based on a fastener definition. And again, we can see those fasteners are created very quickly and easily using this technology. On a manual basis, very, very lengthy, but of course at this level it's very straightforward to do that. And again, in the model browser tree we can see the fastener definitions. So once we've got that local detailed region fully developed in terms of the mesh, the properties and the local fasteners, we now need to tie that into the larger wing box. So again, multiple techniques for doing this, but in this example we're going to look at again how the custom tool palette has been used to develop a simple script which ties coarse to fine nodes together in a manner that gives us load continuity across an interface. So we can look at the free edges and show that currently the fine mesh is not tied into the coarse mesh for this region, which is the upper wing skin. And again, looking in the custom tool palette, we have another auto tie nodes macro or script set up. Pick a series of nodes or bodies, and it looks for the nodes on the free edges and then uses an algorithm to find the closest nodes and then tie them together using, in this case, an RB3 or even an RB2 definition based on the user's input to tie the coarse to fine mesh in those interface locations. If we turn off the model, we can see those discrete ties shown explicitly on screen. We can go into the discrete tie user input box and modify those ties as needed. We could switch them from rigid to compliant, so RB2 to 3. We can change some of the degrees of freedom of connectivity if we wish, but just looking back at the overall model, we can see the interfaces, how they're tied together. If we switch this to rendered mode and take off the element edge lengths, we can see the RBE connections in a much clearer manner. So again, because this is defined using the Python API, we've got full capability to change the connectivity type as we wish. And then we can look at some of the model response. So a simple wing up bend case here. So we've got top row showing the GFEM, top row showing an isometric view of the GFEM versus the DFEM, and then bottom row shows a front-on view. So of course we've got a consistent global response, but at the region of interest where we've dropped in the detailed model, we would have a different response based on the mesh topology. Okay, so looking at solver capability, the Apex Nastran workflow supports linear static null modes and linear buckling. One way in which we could perhaps look at how Apex works from the embedded solver, the Apex structures perspective, and then an external Nastran solution is as per follows. So first of all, step one, we build the model or modify an existing model within the Apex modeler environment, whether that's built from scratch using an orphan mesh approach or a hybrid combination of the two. Then we could, especially if you've got a complex model, a complex assembly with many parts, we could look at an incremental verification of the assembly build. So previous example we saw, we verified one of the wing box ribs before we tied it into the overall structure. We can do that very quickly using the Apex Structures internal solver. We can effectively verify each discrete part within the sub-assembly or assembly level definition to prove its behavior. So once we've got the verified model, we can export to MSC Nastran to develop what we're calling our production level results, where we may have a legacy or a certification requirement to use MSC Nastran. So we'd simply export the bulk data file, model export, solve externally, and then read those results back into the Apex modeler environment for result exploration and post-processing. So that said, those are a number of workflow examples for a typical aerospace environment. Some of the discrete enhancements that we've seen within this Iberian Lynx release, we've got a number of geometry enhancements. So we've seen this certainly in terms of lofting, but we've now got more mature, more evolved CAD type tools such as revolve, extrude, sweep and lofting, which comes in very handy. So looking at this quick example, which is simple jet engine cowling. So we're going to look at revolving the curve at the front that we've just highlighted, and then spin that around an axis. So we're taking advantage of the Apex magic markers, which effectively allows us to pick things like endpoints and arc centres on the fly. Use the rotation axes. We've got full control in a manual sense, and we can see a preview of that surface, and then middle mouse button to accept, and we've got the front of the engine cowling revolved around to give us the surface on screen. So we've got the front of the structure built. So we're now going to look at lofting a surface, so picking a series of non-connected curves, and then building a surface that passes through those curves in a spline sense. We've got full control over edge continuity and what have you, edge tangency, to give us the structure that we want. Geometry from mesh, or the faceted surface creation, which we've looked at with a simple example. So we've read in a bulk data file. We've got no geometry. We can check the shell thicknesses and look at the topology. And what we're going to do here is modify the bulk data file to give us a solid mesh region. So conventional tools would be quite difficult. So what we're going to do is break out the shells in the region where we're going to replace them with 3D elements. Take the CAD out so we can see a hole in that mesh topology. So once we have the mesh that we want to work with, we're now going to create faceted surfaces from that mesh. So pick the mesh, middle mouse button to accept using the defaults in this case. It's built a whole bunch of surfaces created from those original shell elements. And of course, this could be done in an automation sense. We've got flat surfaces, but would work equally for curved surfaces. We've remeshed the structure using a new element edge length, and we've got full control now with this faceted surface geometry if we wanted to generate further modifications, so we could seed that surface if necessary. Key here is the faceted surfaces remembered the underlying shell thicknesses, so we don't need to repropertize. That's taken care of. So we dropped in a portion of 3D mesh geometry. We can glue those components together using the standard glue connector technology, and then run the model. So a very quick way to work with orphan bulk data file definition, and to modify that to modify or introduce new geometry as required. So some of the Iberian Lynx meshing enhancements. So we've got the concept of mesh diagnosis or meshability introduced in this level, or this release. So if you look at a quick example of a tube interface, or a tube bracket, so we can 2D mesh that, or 2.5D mesh, hex mesh that, but some of the element quality isn't that great. So we're going to look at surface meshing these faces to drive the underlying hex mesher in the regions shown. Different mesh across a different region. Now we can now see the fillet regions turned yellow, which means we're not able to mesh that. So we can use the diagnose meshability tool and see we've actually got a mismatch in the edge seeding in this region. So we can just match those seeds up, and the solid turns green again, which means it's hex meshable. We can hex mesh the whole thing, and we can do a quick check on the quality. So we've got a very good quality hex mesh defined very quickly using that mesh diagnosis tool within hex meshing. We can look at edge tie enhancements. So again, we're looking at this jet engine cowling. So we might have some internal stiffeners, which are in a separate part, sub-assembly within the Apex framework or model database, and we can see that we don't have mesh congruency at those interfaces. Still maintaining the unique part definition. So rather than merging all these into one part, we're keeping them separate. But obviously we need to use the concept of the edge tie to tie these discrete regions together. And we can do that. Just wait for the mesh ties, and then now the meshes are tied together between those discrete parts within the sub-assembly or assembly architecture. We look at the edge tie on its own. So for Iberian Lynx, the big change here is that we can now mirror, transform, modify those edge ties as a function of the total model. So we're just going to rotate that model round, or mirror that model round, and then look at the resultant edge ties that generated. So it's mirrored the edge ties as well. So we've got full mesh control at that level, and then we can run analysis for the fully tied model just to show the local behaviour. Incremental surface meshing, and then some of the shell orientation modifications that have been introduced. So we can look at in this quick example, so we've got 4 holes in the surface. One of the holes is very close to one of the edges, so the standard feature mesh definition has not been defined for the hole near the edge. So using the incremental surface mesher, it will mesh the features as it sees them. Here it's found the hole, it's shown it in red, it says we can't fit that washer in, so we can change the washer width, so just decreasing that for that single region and then remeshing the whole structure, and those features are preserved within the full mesh definition. We've got the ring of elements as required. One thing which is very important in an aerospace environment, especially if there's going to be downstream hand calcs, is to ensure element alignment for a given region. So we've got shell elements here with the x-axis originally pointing parallel with the long edge. We're changing those now so they're all pointing parallel with the shorter edge, so just a simple rotation of those element XY orientations to make sure we've got element consistency or result consistency in those XY directions. Nastran Interop enhancements, so we've got ID management, the ability to renumber entities, coordinate system definition, we've got discrete ties now fully supported, so that's RB2s and 3s. So we can look at this quick example. So we've got, again, this tube into a bracket scenario, we've got the hex mesh as shown, and then we've got a bar element representing the tube with its equivalent section shown now. We can use the renumbering, so we're going to renumber the nodes and elements for the hex mesh region, or the hex mesh part within the assembly. Accept the defaults there, and then we look at the exported bulk data file and look at the element and grid IDs, and they're shown in the 10,000 series as defined. We can create coordinate frames explicitly, so we're creating a cylindrical coordinate frame at the parallel with the axis of this tube and defined at the central point of the tube. Once we've got those coordinate frames defined, we can renumber if we wanted to. We can apply loads or boundary conditions. So here we're constraining the internal faces of the tube in the radial system, or the radial direction of the cylindrical coordinate system. So just picking out the faces. Again, very quick to do that with an Apex environment. Middle mouse button to accept, and we've now got that boundary condition defined. We can use a discrete tie, so we've got rigid RB2 or compliant RB3. So pick the faces of the geometry, and then pick the center point of the bar element, or the endpoint of the bar element. It creates those ties explicitly. And again, this is generative, so if you just change any dimension within the model, the mesh and those tie and even those coordinate frame definitions will get updated. So we can post-process in that local system. So just changed to an externally defined coordinate system, and then we can look at the R, theta and Z displacements, vectors are shown on screen now, and we've got full control of that coordinate frame definition. We've got the concept of joints within Apex Iberian Lynx. So rather than building manually coordinate frames, local grids within particular coordinate systems, and then tying all those together with RBE2 or 3 elements, we've now got the concept of joint, which effectively does all of that type of build and connection within a single Apex environment, or a single Apex function. So here we're building an involute joint, which is effectively allowing rotation about the axis of connection and connecting the shell structure into the local bar structure. And again, those entities are developed in the model browser to see the specifics, or to modify the specific if necessary. If we look at the resultant BDF file that's written out, we can see the local grids, coordinate frames and connectivity that's defined, and obviously the Apex solver gives us that response as required. We've got result exploration, so we've got the ability to import Nastran HDF5 result files to probe those results using 0D and 1D probes to develop scalar vector or tensor plots at particular locations, or even over a path, a curve drawn on a model or mesh. And then finally, within this Iberian Lynx release, we've now got the ability to write out those results to an external CSV format, and we can just look at this this structure to show how we could export the bulk data file. We can look at the bulk data file that's created. We can do this on a single file or include file definition. We can run the Nastran result or generate the Nastran results externally, and then read that HDF5 file back into the Apex environment. Just bringing that in, importing the results, and the results are brought in successfully. We can now post-process. So we're going to look at a quick animation of displacement, and then we can look at discrete results. So in this case, we're looking at the beam element section outputs, based on the combined axial and bending stress, and then we can look at using the 0D cursor, so we can pull out discrete results. And again, this is very visual, so you can, very difficult to make mistakes when you can see the output explicitly. We can generate that a table of those probe results and modify the table if we need to, and then write that data out to a CSV file for external post-processing if we need to. Some of the Iberian Lynx customization and automation enhancements. So we've now included scripting support for both analysis and result exploration. Previously we only had it for model build, but now we can effectively black box the whole process by including analysis and result exploration. We've got the ability to custom develop or custom define tools within the Apex environment, as we've seen with one of the earlier examples looking at fastener build. We're just going to look at this quickly. So here we've got a simple example, a simple macro which defines the geometry of a buckling panel under compression. So we can run that script, and we're handling the model build, so mesh, geometry, mesh, properties, loads of boundary conditions, but we're also invoking the Apex solver and result exploration through that automated approach as well. So we get all the way through from a single click of a run script button to having results in the environment with no manual input whatsoever. So this opens Apex up to parametric studies and or the ability for less experienced engineers to take advantage of the full FEA model and analysis capability. So we're just looking at some of the buckling modes here, and we can see we've got a low buckling mode shown in red in the table on the right hand side, and if we wanted to we could rerun the analysis to look at different design setups. So second scripting example here. This one introduces the concept of the custom tool environment. So we've got an Apex strip set up, and the custom tool is set up to read that in by the graphical user interface. So we've got a family of parts here, so we could effectively define this based on all sorts of different dimension and model criteria. But once we've got the inputs that we're happy with, we just press the green button to accept the inputs, and then the model runs, or the macro runs and builds the model. So we've got a sort of flexible tube arrangement here. So building the geometry, so sketch and then revolve that round, mesh the structure, and then we've built the model completely. And then we could have in fact included the analysis and result exploration within this script, but we can see the model response based on those initial parameters. So once we've got this defined, we can we've got full control of the model. The key thing here to say is that Apex really now is a game changer. There's multiple technologies in the Apex environment, which mean we've got a model build, solve, analysis, solve and post-processing capability unseen of before in terms of legacy tool sets, and really now it's open to you to use and to take full advantage of that technology.